I prepared these slides under the impression that these were cashews here in this bowl. I don't think they're cashews, so forgive me. But suppose you and everybody else in your class has been charged with determining the weight of this bowl of cashews. I'm going to call them cashews even though I don't think they're cashews. And you could do that with a bathroom scale, the type of scale meant for measuring body weight. So we're talking about weights, at least as large as 50 pounds, but could be on up to several hundred pounds. If you look here, it says kilograms, so this is really not pounds. Darn it, I just realized that. Let's pretend that this dial is in pounds. Never mind the fact that it only goes up to 120, which is totally unrealistic. Or you could put this bowl of nuts on a triple beam balance, which we're going to see is much more precise. Now, because most triple beam balances report the weight, in air quotes, I'm saying weight, in grams, I want to remind you that 1 pound, well, let me put it this way. Remember, the gram is a unit of mass. If your mass is 80 kilograms, for instance, that doesn't change when you go to the moon. You weigh less at the moon, but your mass does not change. So if you take this many grams and put it on the moon, it's going to weigh significantly less than 1 pound, but this many grams weighs 1 pound on the Earth. Or you could say that 1 pound is a force equivalent to the gravitational weight of this many grams. Excuse me. So suppose you had put this bowl of cashews on the triple beam balance here, and I haven't zoomed in here, but with a lot of these balances, you can determine the mass fairly accurately to the nearest hundredth of a gram, as I recall. I believe, yeah, to the nearest hundredth of a gram. Doesn't look like this one does that necessarily, but okay, so that's why I chose a number to the nearest hundredth of a gram. And if we'd like to convert that into pounds, we would just divide by how many grams are equivalent to a pound. And so that means with this this balance beam, just triple beam balance, that's what I meant to say. Balance beam, that's gymnastics. With this triple beam balance, you could conceivably measure the weight of something like a bowl of cashews with this kind of precision, this many digits. And that's certainly not possible with a bathroom scale. So again, let's pretend that these are pounds, not kilograms. If you stood on this scale, the best you can do is tell which line the needle is on top of. Maybe you could interpolate, meaning if the needle appears to fall between two notches, like let's say it's right here. That's halfway between, let's say, 60 and 61. So you might interpolate and guess, I don't know, 60.5. But that's definitely the best you can do. You can be no more precise than that. So this measuring instrument is way less precise than the triple beam balance. So I just made up some numbers here. Maybe 8 people in the room took turns putting this bowl of cashews on the bathroom scale and estimating the weight. And if this is really the weight of that bowl of nuts, then when you put it on the bathroom scale, you're not going to have these digits at your disposal. The best you can do is come up with a number like 1.5 or 2. If the true weight is between 1.5 pounds and 2, this is really as good as you're going to get. Now maybe if you've got good eyesight, you can tell that the needle is closer to 2 than it is to 1.5, and so you might try to guess something like 1.8. But all of the numbers are going to be basically either 1.5 or 2. Maybe one person will write down 2.5, because keep in mind that that needle, there's some space between the dial needle and the actual dial. And so depending on which eye, like if you close one eye and then switch eyes, the needle will appear to shift a little bit. That's called parallax, which is something very important in this class. But that's why I chose a range of numbers here. On the other hand, with the triple beam balance, if, provided that the people using the scale actually know how to use the scale, if they've been taught how to use it, all of the values are going to cluster around, they're going to cluster in a much narrower range. There's no reason why people should be getting the second digit, or I should say the hundredths place digit, different from their lab mate or their classmate. There's no reason that they should be, unless they're just using it wrong. So everybody's going to agree on these digits. There may be some disagreement in this final digit. So I've tried to choose a realistic range of values here for the possible weights that one might measure using a triple beam balance. And here I've used Excel to make some crude histograms, aka bar charts. Let's first look at the histogram for the bathroom scale. So these various intervals here along the horizontal axis are called the bins. And the bin width looks like it's, let's see, what's 2.1 minus 1.9? That's 0.2. So there's a 0.2 pound range here. And the height of this bar represents how many people of those 8 that I showed you, how many of those people came up with a measurement between 1.9 and 2.1. And evidently I dropped those numbers from the vertical axis, but you can see that the largest number of people came up with a weight in this range. There were a good number that came up with weights in this range, but there's nobody that wrote down a weight of greater than 2.5 pounds or less than 1.5. So it's not the most realistic example, but you can see how coarse this measurement is and how imprecise it is, because there's a rather broad range of possible values here. When we look at the histogram for the triple beam balance, it's much narrower. In fact, it should be much narrower even than this, but I tried to do this in Excel, and if I actually had, see how the left end here is 1.5? If I made this 1.5 and over here 2.5, this histogram would be so squashed in the center that you would barely even see it. So I had to stretch it out a little bit. But the point is that the values are clustered around a much narrower range. And that reflects, excuse me, that reflects the fact that the measuring instrument is way more precise. You can just see it by looking at the so-called distribution of measurements. This is how the measurements are distributed. There's some in the range of 2.3 pounds to 2.5. The greatest number falls in the range of 1.9 to 2.1. That's how the measurements are distributed. Clearly, the measurements are distributed differently when using the triple beam balance. Now, even though the spread is different, in both cases, the measured values cluster around the same so-called mean. So the word mean is another way of saying average. In both cases, the average is around 1.9. So you may be, these people up here may have used a more crude device or less precise measuring device, tool, instrument, what's the best word there? But they still came up with the same average. So that the average isn't affected so much by the precision of the instrument, it's more about the spread of the values. So that's what I've indicated with this arrow here. Now, there are multiple ways to define the spread of the values, the measurements, or you could call it the dispersion, the standard deviation. There are various ways of quantifying that, and we're going to look at just one definition, one very intuitive definition for this lab. But I just chose, like, I didn't have the spread go all the way out to the very edge. It's maybe halfway out, 2/3 of the way out. Average absolute deviation. Well, I haven't defined that yet. I'll get to that in a later slide. But at the very least, you can see that the spread for the more precise device is much lower. So the more precise the measuring instrument, the smaller the range of deviations, or the deviation of the various measurements. And that's why this number is so much smaller. This is in the 10,000ths place. This is in the tenths place. And I went with 0.2 because if the actual weight of the bowl is around 1.8, 1.9 pounds, and there are plenty of people who wrote down 2 or 2.1, the difference between 2.1 and 1.9 is 0.2. That's why I chose the number 0.2 for the typical deviation of the various measurements from the average of all the measurements. It wouldn't make sense to go with, let's see, 2.5 minus 1.9 is 0.6. It wouldn't make sense to choose 0.6 as our number quantifying the spread of the data, because that's the greatest difference between any given measurement and the mean of all the measurements. It would be better to pick a more typical value of the difference between the measurements and the average of all those measurements. Okay, so again, clearly this top measurement is less precise. It's made with a less precise measuring instrument, and this one is much more precise. Now here's the term that you'll see in the lab report, or the lab handout for this distance and angles lab, relative uncertainty. And keep in mind that the vocabulary I'm using here is not 100% standard. You may see the term relative uncertainty used for a slightly different purpose elsewhere, maybe in a class that you take in the future. In fact, I use this term to mean something slightly different even in other classes that I'm teaching right now. Okay, a larger relative uncertainty. What I mean by relative is the thing that we're measuring is around 1.9 pounds. With this instrument, many of the people measuring the bowl, or the weight of the bowl with the cashews in it, were off by around 0.2 pounds. So relative captures how big the average deviation is compared to the thing you're measuring. So 0.2 is rather large, rather significant compared to 1.9. It's definitely more than 1%. In fact, what is that? That's almost 10%. I think that's more than 10%. On the other hand, when we go down to the triple beam balance measurements, the average person is in error by a 10,000th of a pound. 10,000th of a pound is really insignificant compared to 1.9 pounds. So we can say that this measuring instrument is much more precise, and by the same token, the relative uncertainty in any given measurement is considerably smaller than it is with the bathroom scale. So just to summarize, if you put this bowl of nuts on a kitchen scale, you could be off easily, or the reading that you get from the scale could easily be off by 0.2 pounds. That's more than 10% of 1.9 pounds. So you could easily be off by 10%. If you're off by 10% when using something like the triple beam balance, that means that you did not use the scale correctly, or it's broken, or the manufacturer screwed up. So it's supposed to be a much more precise measuring instrument. Here's a graphic I just pulled off the web that's a little clearer. Let's not get too attached to these numbers, but some quantity has been measured here a bunch of times with two different instruments, and you can see that the range of values, they cluster about the same mean. They've gone with the mean of 1.0, but the spread in the measurements is much larger over here, and that's why they're saying that this measurement was imprecise as opposed to this measurement over here, which is precise because the spread of values is much smaller. Okay, so right now I'm using this symbol delta x loosely to mean the spread of data. You know, I chose to go from, why is my computer getting slow here? Okay, I chose to go from the center of the distribution, or the mean, about halfway out to the rightmost edge. All right, so it's just very qualitative here. X average is the center of the distribution. Now the relative uncertainty, I just introduced that in a previous slide, but here it is more clearly. You take the spread and divide it by the average value. So the previous example was, for the bathroom scale, the spread of the measurements was around 0.2 pounds, and you just ask, how does 0.2 compare to the thing we're measuring, which is 1.9 pounds? You just divide. It's a ratio. And of course, you could turn that into a percentage by multiplying by 100. So just a few more slides here. Let's consider a very simple example of 7 measurements made of, I'm not even going to make up an example. You measured something 7 times and you came up with these values. Maybe 7 different people measured it, and it was a very imprecise measuring device, and that's why these numbers are so different. First, let's calculate the average. Let's review how to calculate the so-called arithmetic mean of a set of numbers. Since there are 7 numbers, you add up those 7 numbers and then divide by 7. You just divide by the number of numbers. Okay, and x bar, that's a very succinct way of writing the average value. So notice I'm using subscripts to distinguish the various measurements. x5 is person 5's measurement. Excuse me, x bar means the average of all those measurements. So I find that when I add these up and divide by 7, I get the number 21. And here's a way of representing that symbolically. Some of you may not be familiar with this notation. This capital Greek letter sigma. This is capital sigma with a subscript I. It means sum. So it means add up all the various x sub i's. I is an index that can mean any number in your set. It could x sub I could mean x1 or x4. So sum over I means add up all of the x's, x1 plus x2, etc. And then divide by capital N, and I'm using capital N to mean the number of measurements. So that's just a symbolic way of expressing how to calculate the average for any set of numbers. And now I will formally introduce this term deviation. So if a measurement deviates from the mean of all the measurements, that just means it's different from the mean. Just take the word literally at face value. So, for instance, we've already calculated that the average of these 7 numbers is 21. Clearly, measurement 1 deviates from the mean. It's lower than the mean, so you take the number you're talking about, subtract the mean, this would be the deviation. So, measurement 1 deviates from the mean by -4. That just means it's 4 below the mean. Measurement 6 is obviously higher than the mean. What is the deviation? Just take measurement 6 and subtract the mean. It deviates from the mean by 2, so it's on the high side, whereas the previous measurement was on the low side. So, can we somehow, if we were going to pick one number that represents how spread out the data are, how do we go about picking that number? Because some of these measurements deviate from the mean by more than other measurements. Like this one deviated by -4. Notice that measurement 4 doesn't deviate at all. In fact, it's equal to the mean. So what can we do with these various deviations to come up with a single number that captures the typical deviation of each measurement from the mean? Well, probably your first thought is, why not just average all the deviations, right? Some are lower than others, some are higher than others. Let's just take the average of all the deviations, and that should be a good number that represents the average deviation from the mean. So let's see what happens when we do that. Here's a table with my the 7 measurements, and I've listed here all of the deviations from the mean, and you can actually see this in your head. When you add these up to calculate their average, we've already averaged the measurements, right? The average of these measurements is 21. If you want the average of the deviations, you would have to add them all up and divide by 7. But when you add them up before dividing by 7, you get 0. Of course, 0 divided by 7 is 0. So the average deviation is 0. And that's not just a coincidence. It's not a consequence of the particular numbers that I picked here. That will always be the case. Some of your measurements will always deviate in the positive direction from the mean. Some of them will always deviate in the negative direction. That's how the mean works. It's supposed to be in the center of your distribution. So if we go back here to this graphic, obviously this data is more spread out than this data. But if we use the average, if we calculate the average deviation for each distribution, we're going to get the number 0 in both cases. So that number, that quantity, average deviation, evidently tells us nothing about the spread of the data, because you'll get the same number whether you apply that formula to this imprecise measurement or this distribution or this precise distribution. So we need some other quantity to capture just how spread out the data are. And maybe you've already thought of a solution. Yes, some of the deviations are positive, some are negative, and that's why they cancel. What if instead of adding up the deviations, we first take their absolute values, perhaps? Yeah, some are positive, some are negative. How can we fix that? Well, if you take the absolute value, that makes all these minus signs go away. Let's say we don't really care whether a number is on the positive side or the negative side. We just want to know how far it is from the center. Then we're really just talking about absolute value. So now I've repeated this table, but I have a fourth column where we just take the absolute value. Remember this symbol for math? This means absolute value of the deviation of the ith measurement, where I runs from 1 to 7. It's really simple, right? You just get rid of the minus signs. And then go ahead and average that. So if you average all of these, what I'm going to call absolute deviations, average the absolute deviations from the mean, you get this number 2. which is very reasonable because some of the numbers, in fact, two of the numbers are 4 pounds away. Well, not pounds. This is my made-up example without units. The average was 21, right? Two of the measurements were 4 off from 21. A couple of the measurements were only 1 off. One of the measurements was on the nose. There was no deviation. So 2 does seem like a reasonable number to describe the typical deviation, absolute deviation from the mean. So this is what you'll be doing in the lab, because remember, you're going to make 5 measurements of the angular size of something like a soda can, and you'll convert those angular sizes into actual heights in centimeters or inches, and you will be calculating the average deviation of those measurements from their mean. And then you have to repeat that whole procedure for the other object, your doorway or music stand, whatever you've got. Tree. A tree's not good because how are you going to measure the height of a tree? It's got to be something for which you can actually measure the height with a measuring tape or ruler. So here's a formula, a symbolic formula for this quantity that I'm going to call average absolute deviation. It instructs you to take each measurement, the ith measurement, where that could be x1, x2, etc., and from that measurement subtract the average of all the measurements. So first you have to calculate the average of the measurements before you can use this formula. So this quantity is what we call the deviation. Put these bars around it. Now you're talking about the absolute value of the deviation, which I'm just calling absolute deviation. Lastly, add up all of those absolute deviations. In this case, that's 7 different absolute deviations. Divide by the number 7, and that will give you the average absolute deviation. Again, this notation is not standard. I just picked a simple notation for the purpose of this lab. Many of you have taken a math class or a science class where you've heard the term standard deviation. Not absolute average deviation, but standard deviation. That's a very closely related quantity. Just a moment ago, I didn't want to worry about sign, whether deviation was plus or minus. So my solution for getting rid of the minus signs was just to take the absolute value. But you're aware of another way of turning a negative number into a positive number. What you could do is just square it. Like negative 4 times negative 4 would be positive 16. So another way to go about this would be to square all of the deviations and then calculate the average of the squared deviations, and lastly at the end to take the square root. So that's called the root mean square deviation, or sometimes it's called a standard deviation. It's not that much different than what we're doing, but you don't have to worry about that. Let's just stick with this straightforward quantity where you just take the absolute value of all the deviations. So I extended the table of fictional bathroom scale measurements. Here's a whole set of possible measurements. The average is 1.9, like before, and then I calculated, so I'm using the letter W for weight, and then I calculated delta W, that's the deviation of each measurement from the mean. So all of these numbers have an average of 1.9. 1.5 here is 0.4 below the mean. So this particular measurement deviates from the mean by negative 0.4. I did that all the way down, and then I just calculated well, there's no calculation really, just get rid of the minus signs. So here are all of the absolute deviations, or the absolute values of the deviations, and then you simply average these. Now, you're not going to have to deal with this many numbers, right? You're just doing 5 measurements for your near object and 5 measurements for your far object, so it shouldn't take that much time. And I find that this set of numbers has an average absolute deviation of 0.3. So is that a precise measurement? Like, how bad is that? Well, the thing that we're measuring, we think it's around 1.9. That's our best estimate because we took the average of all those different people's measurements. But on average, each measurement deviated from the mean of 1.9 by about 0.3 pounds. How bad is that? Well, to answer that question, you just take the ratio. So I'll call this the average absolute deviation. How does that compare to the average of the weights, 1.9 pounds? Just take the ratio. So that's what I'm calling relative uncertainty. The average uncertainty was, my laptop is really giving me trouble here. The average uncertainty is 0.3 or I said uncertainty just now, but I should be more precise. The average absolute deviation was 0.3. And if I divide that by the weight, I get this ratio, 0.16. Let's turn that into a percentage. And it's called relative because you're taking a ratio. How does 0.3 compare to, how big is it compared to 1.9? After multiplying by 100, of course, you find that that's what I'm calling a relative uncertainty of 16%. So in your lab, you will average your 5 measured heights using the finger rule for like the soda can or whatever you're using. And then you have to calculate the deviations of your 5 measurements from the average. And then average those absolute deviations and then divide that by the average height that you calculated to see just how imprecise your measurement is. Now, since you're using this finger rule, I'm not expecting it to be particularly precise. Maybe your relative uncertainty comes out to be 20%, 30%. You don't need to fake the numbers. If it comes out to be 100%, you probably did something wrong and you should review your method. But I'm expecting a rather large relative uncertainty. Do your best, but there's no need to fudge the numbers. Now, when you repeat this with the far object, you're still using the finger rules, but keep in mind, you're going to be measuring something that's significantly taller. For instance, a doorway, maybe even, I don't know, like from the ground to the eaves of it, like the gutter of a one-story house, if you're able to do that, maybe a ladder. So the thing that you're dividing by will be a bigger number, and that may bring your relative uncertainty down. That's something to watch for. As you go into it, which measurement do you expect to be more precise? Your measurement of this Coke can sitting on the kitchen counter or your measurement of something taller? Okay, so it's not a very involved lab. It's just to get you familiar with this relation between angular size, distance, and actual size, linear dimensions, and to get a little practice manipulating these numbers. The last thing you'll have to do, remember I said that after you've finished estimating the size of the Coke can with your finger rules, actually take the ruler, walk up to the Coke can, put the ruler next to the can and measure it that way, which is obviously going to be a more accurate measurement. So call that measurement the, quote, true value. Now, if we go back to the example of the cashew bowl, let's pretend that this is the actual weight. Maybe we had some super precise chemistry scale, so we knew what that value really was. Here's how to calculate the percent error between your average weight and the true value. Remember, you're going to have 5 measured heights of the Coke can using the finger rule. Take the average of those 5 measurements, call that your best estimate using the finger rule. How bad is that measurement? I mean, obviously, you should be curious about that, right? Like, does this actually work? If you're really careful using the pinky rule and you find that the average height that you calculate using that method is off by 50% from what you get by just using a ruler, well, then it's not a very good method, is it? I think you can do better than that, though. I think if you're careful with each of your measurements, you'll have a smaller percent error. So this is how you do that. Suppose that your average measured weight with the kitchen scale, or excuse me, the bathroom scale was 1.9. You just take your experimental value, I'll call it, subtract the true value. Don't forget to use the absolute value. And this is where you might want to hit equals in your calculator. You just do subtraction, hit equals, and then divide by, what is my laptop doing? And then divide by what you consider to be the true value. Lastly, multiply by 100 to turn that into a percent. So I found that my made-up numbers for the weight of the cashews, my fictional value for the average of all those measurements was off by about 1% from the so-called true value. So I will be looking to see that you did this correctly in your lab. You want to know what's the percent error between the average number that you got from your finger rule method and the more accurate number that you can get by just measuring the near object directly with the ruler. And my last comment would be, hopefully, the percent error comes out less than your percent uncertainty. So if I just back up real quick. Yeah. Let's pretend that the measurements we're discussing here are your measurements of the Coke can. If you find that the Coke can is, I don't know, 5 inches tall using the finger rule, but that your relative uncertainty is 20%, what that means is you think it's 5 inches, but it could be anywhere between 5 inches plus 20% or 5 inches minus 20%. You think it's somewhere in that range. So if you then take out your ruler and measure it accurately, and you find that your percent error is 15%, that's a really good thing, because your percent error, the error between the true value and the value that you came up with in your finger rule, is that value is less than your uncertainty. That's a good thing. If your percent error is much greater than your relative uncertainty, then that tells you that something went wrong in your process. You probably goofed one of your measurements, or perhaps you didn't calculate things correctly and you want to review your numbers. That's it.